Look at the daily fluctuations of a stock market index, or the monthly shifts in global inflation. The data jumps, spikes, and plunges. To the naked eye, it looks like a meaningless, chaotic mess. But as Professor Gower often points out to his econometric students, this chaos is not a failure of the system. A specific type of mathematical randomness, known as white noise, serves as the structural core of all time series analysis. To accurately predict the future path of an economy, we must isolate this purely unpredictable component. Without it, the mathematical tools used to estimate relationships lose their efficiency, and the resulting estimators fail to reach the standards required for reliable forecasting. The difficulty lies in the fact that not all messy data is truly random. Pure, usable chaos requires incredibly strict mathematical isolation before it can be used in a model. Mathematical randomness provides the baseline required to isolate and identify the systematic patterns driving an economy. Professor Gower uses a dartboard analogy to illustrate this baseline. Imagine throwing darts while blindfolded, where every strike is entirely independent of the last. These uncoordinated impacts represent the random shocks entering an economic system. Econometricians denote these shocks with the Greek letter epsilon, or U sub t. For a sequence of these shocks to officially qualify as white noise, they must pass 3 rigid tests. First, zero mean. Positive and negative shocks must cancel out. Second, constant variance, or homoscedasticity. The overall spread of these random kicks remains within a constant width. Finally, no autocorrelation. A shock today provides zero predictive information about tomorrow's shock. Only when a sequence of data clears these 3 filters does it graduate to the title of white noise. It becomes a pristine, unbiased variable, ready to interact with complex dynamic systems. Think of white noise as a raw energy source, and time series models as the filters that direct it. These models dictate how raw shocks are delayed, smoothed, or recycled to create the recognizable patterns we see in the real world. Moving average models carry shocks forward for set periods before their influence vanishes instantly. Autoregressive systems recycle past shocks via Wold's theorem, decaying gradually over an infinite horizon. In a random walk, the system stacks every shock permanently, creating a wandering, non-stationary trend. By identifying these different ways that raw noise is filtered, through finite lifespan, infinite decay, or total accumulation, we can explain why economic data shows such distinct levels of persistence. Returning to the econometrician's desk, we see how this theory is put into practice. White noise provides the standard for determining if a model is complete. After an ARIMA model extracts every identifiable trend and cycle from a dataset, the residuals, the leftovers, must align with the 3 rules of white noise. If any pattern remains in those residuals, the model has failed to capture all the systematic information. Econometricians distinguish 2 distributions. Left is strict white noise, where independent shocks follow any shape. Right is Gaussian white noise, forming a symmetrical bell curve. This curve calculates probabilities, deciding if a shift is a trend or a significant outlier. A successful model is one that strips out every available signal, leaving behind nothing but this pure, uninformative randomness. Defining this chaos mathematically provides the essential baseline. It is the only way to prove we have successfully mapped the predictable world.